Thank you very much for the invitation and for the opportunity to present here. It's nice to see some familiar faces or names, at least, in the chat. I'm going to say a little bit about where we come from, and then I'm going to talk about PyPSA for the rest of the talk, because I am, so my name is Harry van der Weijden. I'm the head of research for open energy transition. If you haven't heard about OET before, we're a relatively new nonprofit with the aim of essentially doing what Peter just introduced, to have more impact with open source models. There are plenty of organizations that are happy to use open source models, but they also want support, and they want someone to help them with implementation and with the software engineering side. That's what we aim to do. So we perform planning studies ourselves, but we also help clients use open source software and open data, and we provide support and training for that. We work with, for instance, with TSOs. We have a project now with NSOE to look to see if we can use PyPSA for its Indian network development plan, but also for regulators and for commercial clients, for instance, battery operators who want to use open source models to see where they have 24/7 access to green energy. And we're a German non-profit, but we have people all over the world, fully remote company working together on tools. We're not PyPSA fanboys as such. We use a range of different tools. We also have people who do Gen X modeling, for instance. We have Times experts, but PyPSA at the moment is the core of what we do. I want to address three things in this presentation. I want to say a little bit about the electricity system modeling landscape and how open source fits in that, because I don't think everyone in this call is an electricity system modeling expert. Keep that brief. Talk about PyPSA and where we are currently, and a little bit also about our development plans. So first of all, electricity system modeling and why PyPSA kind of fits in. So there are different types of electricity system models. You have the more real-time models, which are generally nonlinear models that model the operation of the system and do, for instance, reliability, power quality assessments, these kinds of things. Then market models, which are more medium to long-term models, and long-term investment models to do capacity expansion or future scenarios and those kinds of things. And there are a number of proprietary tools which are used for these different applications. Plexos is probably the most famous one on medium to long-term planning. It's also the tool that's used, for instance, currently by NSOE in the 10-year network development plan process, but also used by many TSOs. And for real-time models, there are other tools such as Biofactory or PSSC. PyPSA at the moment focuses mostly on this medium to long-term modeling, so hourly or even coarser resolutions. There's no real reason why PyPSA could not be used for real-time models. There is capability to do AC modeling, as I'll show in a minute, but the focus so far has been mostly on medium to long-term planning. And there are other open source tools that do more on real modeling. There's a couple of examples here, but there's also Panda Power and other packages. And then if we look at actually, there are these different tools. There are proprietary tools and open source tools. These proprietary tools have by far the largest share of the market. Tools like Plexus have very expensive licenses that cost definitely 6 figures to begin with. And open source tools are coming, but they still have a very small market potential. That's because until now there was a relative lack of support. The software engineering, many of these packages were developed for academic purposes, not necessarily for commercial purposes. So the software engineering best practices have not always been applied. And there's also just missing awareness and knowledge that these tools exist and that they can do the same thing as proprietary tools, but we're doing our best. And what we try to do as OET is make sure that these things that are holding back open source solutions are solved so we can give support. We're working on software engineering best practices, etc. But we're still the David against the Goliath of the proprietary tools such as Plexos. But open source energy planning is coming. If we look at PyPSA, for instance, as probably one of the most widely used tools, we see more than 500,000 downloads per year. from our GitHub repositories, and increasingly we see organizations using PyPSA as well, and starting to use it either in addition to proprietary software or as an alternative. So here's a long list of organizations that we, as OET, for instance, work with, and that are already using these tools. So and they're using them all over the world. So what is PyPSA, or what can PyPSA do? PyPSA at its core is an open source toolbox for simulating and optimizing power and energy systems. PyPSA can do more than just power. In this talk, I think I'll focus mostly on power. But there are sector-coupled versions of PyPSA which can also model gas and other parts of the energy system. PyPSA is probably one of the most widely used tools for power systems modeling, one of the widely used open source tools anyway. Just to give you a little bit of sense, here's the history of number of times that people have clicked star on GitHub. So PyPSA has been around for a while, but especially in the last couple of years, we've grown definitely more than linearly, and there are more and more people using it. So there is momentum, which is great. For all the reasons that Peter just mentioned, it just enables more collaboration, more quality, and lower costs. With PyPSA, you can do, if I start on the left of this slide all the way at the bottom, you can do power flow modeling. You can do nonlinear power flow modeling as well. It's not just DC approximations. You can do market modeling with all the complications that you want, such as security constraints, unit commitment. As well, you can have models that run in series so that you do a day-ahead model followed by an intraday model. And for longer term problems, you can also use the capacity expansion functionality that PyPSA has to invest either in a rolling horizon way or single horizon. And there are packages to do things like Monte Carlo simulation, to do MGA, and various other options. So most of the things that you would want to do with a electricity system model, you can do with PyPSA with using the built-in functionality. If you look on the right side of the slide, the components of a model, it's the typical components that you expect in an electricity or an energy system model. So you can define your generators with unit commitment decisions. Time series and PyPSA are customizable. Most users will use hourly resolutions, but there's no reason why you could not do 15-minute resolutions or weekly resolutions. You can have AC and DC transmission networks. You can have storage. There are storage modules for different types of storage. If you use sector-coupled versions, you can also model the conversion between different energy carriers and model things like EVs separately. Just to also give you a sense of how fast these models are. If you solve, for instance, an electricity sector-only model for in Europe with a relatively coarse resolution of about 110 nodes, so a few nodes per bidding zone at a temporal resolution of 3 hours. That's the kind of thing you can do on your laptop at home. So in less than an hour, and with memory usage that probably fits on the laptop you're currently using. If you want to use the sector-coupled functionality, so if you want to model different energy carriers and the conversions between them, then you are looking at much more memory use and also much higher solution time. So that you know, if you want to do that with PyPSA, you also need to be looking at either cloud computing solutions or high performance computing. Just to get a little bit more technical about existing technical capabilities. So looking not just at what PyPSA does, but looking at the backend. So PyPSA in its current version uses a Linux framework to communicate with the solver. Previous versions of PyPSA were using PyOMO, but we found that that was much more memory intensive and also took a much longer time to process and communicate with the solver. So we're now using Linux, which scales very nicely even with very large networks. Using NetCDF as data containers, which is interoperable with a large number of other things that you might want to do with the data. PyPSA, as the name suggests, is coded in PyPSA, so you encoded in Python, so you're using Python. using pandas data frames. So you can also very easily interact with the whole Python ecosystem of tools that you might want to use, for instance, to visualize data or to do pre-processing of data, or with other models that exist within the Python ecosystem. There are network reduction and temporal clustering methods as well included within PyPSA. So you don't have to do that manually. You can do that using built-in methods. And of course, there are interfaces to major solvers, such as Gurobi or Cplex, but also to open source solvers such as Hives, which is one of the upcoming open solvers, which we think, especially in the future, are going to be a good alternative for commercial solvers. And PyPSA is highly customizable. It's an open source Python model. You can do what you want to do with it. On the right-hand side, just an illustration of how this framework is built for performance. So for instance, for flow modeling, we're using relatively new methods to make sure that we can do OPS for a large network very efficiently. So we can be up to 25 times faster than basic methods. And this is what you get in an open source model, that you have a lot of people collaborating together and implementing the latest techniques. Now, PyPSA itself is the equations, if you want, so the framework on which you build models. Of course, you need to put in data to do anything useful with the model, but we also have repositories that already come with data. The currently probably most developed one is PyPSA Europe, which is a sector-coupled open optimization model of the European energy system, as you see in the picture. So this includes a workflow to build a PyPSA model for Europe from open data. So you don't have to go looking for your own data, but you can use PyPSA Europe pretty much out of the box, including data collection and collecting data about pretty much all AC lines at and above 22 kV in Europe, but also the existing power plants, time series for demand and time series for renewable availability, and methods for model simplification, such as clustering and network reduction. As I said, PyPSA Europe is sector coupled. So if you don't want to limit yourself to just modeling the power system, you can model. If you have access to cloud computing resources or to high performance computers, you can model the whole energy system with PyPSA Europe. And again, that includes the data that you need for that. If you're outside Europe or you're interested in working on other countries, you can look at the PyPSA Earth repository on GitHub, which takes the same PyPSA framework, but has an automated model workflow to build energy system models, again, sector-coupled energy system models for the rest of the world. So with this, you can model any country in the world. And again, it includes data for many of these countries. Previously, this was electricity only, but there's now a sector-coupled global model. So you can build a sector-coupled model for any country in the world with PyPSA Earth. And then coming on to PyPSA development plans. We are not doing PyPSA development by ourselves. Of course, it's an open source model. Anyone can contribute to the PyPSA Europe repositories and suggest improvements. We're also working together with TU Berlin very closely, who are also co-owners of the repository. But here are some of the things we are planning. One of the things we're currently working on is to have stochastic multi-stage optimization by default within PyPSA. So that's an ongoing development. We're also thinking about decomposition methods. Here I have to explain a little bit more detail, perhaps. So we are within OET developing a cloud compute app, so that modelists that use PyPSA, but also modelists that use other models can very easily use cloud computing resources such as Amazon Web Services or Google Cloud, without having to do any coding, but just by adding an option when they execute a model to not execute it locally, a cloud computing resource. And we are thinking that that's also the place where we can integrate decomposition methods. That would mean that users don't have to do a lot of customization on decomposition, but they can hand that problem over to the OET Cloud Compute app who will decompose it, send it to cloud computing resources, and then return a solution back. But we think that especially when we do stochastic optimization, we could really use decomposition methods, but we also want to make this as easy as possible for users. There is a sector-coupled model, but the gas flows are relatively simple. We are working on making the gas system within PyPSA more realistic to model things like line pack, which the current transport model for gas does not. And we also want to improve interoperability with other tools, so that data from other tools can be converted into a PyPSA data set, but also a PyPSA data set can be converted into other tools. I'll say a little bit about that in a second. In terms of the backend, we're working on stability improvements. There's still some work to be done there, but we're also working on implementing best practice software engineering. I already said earlier, a lot of these modules within PyPSA were developed for academic purposes. We are doing things like making everything more modular, so that, for instance, if you want to swap out a particular your EV model, for instance, with another EV model that you've made yourself, you can do that much more easily. But also adding software engineering things like unit tests for all the different units, having function documentation that documents all the functions in the model, etc. So making it into a mature software package that can really compete, for instance, with Plexos. In terms of front end, we are also doing some work to improve the user interface. There are a lot of users who want to use open source tools, but also want to be able to, for instance, interrogate scenarios in a visual way without having to do any coding. So that's something we're working on as well. So an easy user interface for people who are not modeling experts but want to use PyPSA to do analysis. And of course, we're working on data. So PyPSA Earth data comes from a roadmap. We are working on good validation data, so country level validation data. If you can help us with this, so help validate data for a particular country against other data sets that you know to be valid, please let us know. And in general, we're working on improved automated data collection and integration with OpenStreetMap, so that we can scrape open source data for any country in the world as reliably as possible. What we also want to do is add more policy detail. So having good data about policy targets, for instance, things like renewable targets, regulatory constraints within countries. This is ongoing work. Again, this is something we could really use help with if you're a country expert and you can help us add this type of data for your country or for your part of the world. I said I would say something about interoperability. So there are existing converters that import or export PyPSA files to other packages. Many of these are public as well. One important one that we're missing is converters for Plexos, which is probably the proprietary competitor to PyPSA. So this is also something I want to draw your attention to, and if you can help us create converters for Plexos data, that would really make it much easier for parties who are currently using proprietary software to switch to open source solutions that we can all work together with. And finally, where are we applying PyPSA? So we're currently working with N2E on building essentially a parallel modeling infrastructure for the 10-year development plan to try and see if we can use PyPSA to replicate, first of all, the 2024 TYNEP, and then to look forward to see how this could complement existing tools. For instance, allowing parties who don't have Plexos licenses to participate in the process. Where we are using it for a flexibility needs assessment for a major European regulator. We're using it for cost-benefit analysis and market analysis, for instance, for storage operators. People have also used PyPSA for many other things, such as energy technology design assessments for things on the scale from individual homes to continents.